Hello and welcome again to FEM Expert. In today's tutorial we're going to show you how to perform the modification of the model behavior in a mass spring model using Ansys APDL. This is a continuation to a previous tutorial in which we utilize a suspended mass of 25 kilograms on a spring with a stiffness of 25,000 newtons, and we've seen in this previous tutorial that the model behavior omega depended on the stiffness of the structure and the mass of the structure. So in order to modify that, I'm going to show you how to perform multiple simulations to analyze the behavior, and this is very useful. These processes and the options we're going to use today, they're going to be very useful for you in order to analyze complex behaviors of structures in the future. So we have here the Ansys. This is the tutorial that we had the last time, in which we were creating the structure, we were analyzing it, and we were obtaining the model value. So the frequency, the model frequencies, here we have the first two, they are not of our interest, and the third one is 5.039, which was our interest frequency, which came from 25 kilograms and 25,000 Newton meter of stiffness. And you have here the calculations. If you haven't seen the previous tutorial, we recommend that you go and look at that first one, and then you will be able to understand more in detail the processes and the things that we're going to do in this one. So I'm going to pull this text here. This is basically a copy of the previous tutorial, but we started using some more options. So the idea here is, let's say we want to try to see what are going to be the model results for a variety of stiffnesses from 1,000, 2,000, 5,000, 10,000, 25,000, 50, and 80. You can put more. I just selected 7 because it was easier. So how we would do that is we would have to go to parameters and start working with array define arrays. So we have to go to define edit. And here we can define any array. For example, you can define an array called stiffness. So this array can be an array, it could be a vector, it could be a matrix, it could be a 3D matrix, but for right now we're going to use this as an array, just a stiffness array of 3 variables. I'm going to make it simple just for the example, so you actually understand what we're doing here. So on the stiffnesses, after you create the variable, you go and it says it's a 3 by 1 dimension, it's an array, so you go and edit, and here you can put 1,000, 2,000, and 3,000. Then you go to File, Apply and Quit, Close. So we have this stiffness variable. If we go and list the log file, and we look at the log file at the end, we're going to see that it used this command line, so Deme stiffness array 311, and then it set the values for each one of these, which one of the vector variables, meaning the vector has 3 lines, or it could be 3 columns. It depends on how it's arranged, but it doesn't matter. So for the 111 position we have 1,000. For the 211 position we have 2,000. For the 311 position we have 3,000. We're not going to use this variable. But we're gonna. I used it here so you understand what we were doing, what I was doing here. So the Deme command, it dimensions an array. There's a couple of array types, but we're gonna just look at the name. FRS is gonna be the frequencies that we're gonna obtain, the results of the frequencies, and then we can type array, because it's a type of array, and the number of the dimension. For example, 711. If I hit OK, what this would do is, if we go to arrays parameters, array parameters, define edit, it defines this array FRS. I named it FRS from frequencies. So if we look at edit, it's empty. One other way you can define the values of these variables is doing like a vector. FRS of 1 is equal to 1. You don't have to use the other 2 variables because we don't need it, but even in case you would have a more complex matrix, you would have to put 1, 2, 1 or 1, 2, 2, depends on what you have. So FRS of 2 is equal to 2. And if we go back again, define edit, we look at FRIS, we have 1 and 2 on the first two positions. So I'm going to delete these variables because we're going to use these command lines. And I'm going to do this, copy this, and copy this. And then we're going to look at the array defined edit. So we have two arrays. One is the frequencies, which is empty. It has 0, 0, 0, 0, 0. We're going to keep it like that. And then we have the stiffnesses, which are the stiffness values we want to analyze. 1,000, 2,000, 5, 10, 25, 50, and 80. This is exactly what we define here, because we defined these arrays, the stiffness, and this is a name, so it could be any name that you want. And then we define the values of the stiffnesses this way. Now what we want to do is define perform a simulation with the stiffness 1,000, then another one with 2,000, then one with 5, then 10, then 25, and get the results so we can analyze them. In order to do that, we will have to do a loop. The loops are done with the asterisk do command in Ansys. So for example, if you have asterisk do, comma, you have the parameter. You can have any parameter, it will be called parameter. And then you do from the first value from 1 to 10, and the increment by 1 by 1. What would this do is go on each parameter, like I'm gonna call it another name, pp, from 1 to 10 ppr here, from 1 to 10 to 1, and it will go ahead and give the value 1 to ppr, or in this case here in the text, it will give the value 1 to a, then it will give the value 2 to a, and so on until it finishes the whole loop. So what I'm doing here with this do is I'm saying do a from 1 to 7 to 1, and I'm changing the value of the second real number, the one that was assigned as being the stiffness of the spring. But instead of assigning it with a value, I'm telling the routine to change the real number, or define the real number 2, the real constant number 2, so real constants at a delete. If we look at set2 and go to edit, and we look at it as beam 14, we see that the spring constant is 25,000, right? So what I'm telling the program here is change the real value of the constant 2 to the value of a stiffness A. And since A is going to be from 1 to 7, it's going to do it for 1,002 and so on until all of the values of the vector stiff. Then I'm going to solve each model. So it's going to assign A equal to 1, it's going to solve the model, and then we're going to use the get frequency mode command. The asterisk get, it's a command that's asterisk get. Actually, I would advise you to read about this. Asterisk get, it's a very complex command that allows you to obtain information from the models. I'm going to look at here. It's actually get scalar data, and you can have multiple options from multiple things. Here we could have model results, model results, and you can give it a name to this parameter, or you have to give it a name. I'm going to give it A, so it's obvious, and I'm going to get the frequency from the third mode number. If you put the ones before, it's going to be 0. Then you hit OK, and if you look at the parameters, the scalar parameters, A, it's 5.0. It coincides with this value. So in order to obtain that value, we will have to get this. You can look then at the list. The help of the get command is quite extensive, but it's relatively simple to use. It's get, comma, we have the parameter name, then we have mode, then we have the number of the mode, and then we put frequency for the variable. And that's what we did here, get frequency, we call it FREQ, which is not, yes, FREQ from frequency, the mode, third, and we got the frequency, FREQ. This name and these don't have anything to do. This could be any name, like you can see here, it's AAA. I just used frequency because it was easier to relate to it. So Then we're going to say the FRS. So each one of these vectors from the matrix FRS, because remember we defined FRS as a vector. So we're going to say that FRS of A, so FRS of A is going to be the first value of FRS, is going to be equal to the value that we just obtained from the get command. So we're going to say that we just obtained this A, which is equal to this, and we're going to introduce this value, which would be in our case frequency, to FRS of A, which would be the matrix, the vector with all of the results of the frequencies. Hopefully you were able to understand it. So I'm going to show you then what we'll do is go and hit the asterisk end do. This defines the end of the do command. So the program would be basically performing all of these tasks up to here. It would be done once, and then it will do 7 times the modification of the stiffness, solving, it will get the value of the frequency, and it will store it in our frequency results vector, then it will undo it, and it will finish this 7 times. So we're going to copy this up to here, and we're going to see what happens. I'm going to hit OK. And we have 7 times the solution is done. If we want to look at the model is exactly the same. In this situation, if we want to check it, the real constant should be of a combination 14, should be the last value that we define, 80,000, which is correct. And the last thing we would have to do is to check those values, right? There's 2 options. One of them is not very good in Ansys, so I would advise you to use Excel or other plotting programs. So we can go here and do plot. We can do list. We can do others. We can do parameters, and wait, sorry, I have to minimize the window because I made a little mistake. So here it's going to tell you the parameters, but we don't want that. We want list, others, name parameter, and we would like to select frequencies, and here we have 1 to 7, and we have to get rid of all of these other values. At least in our case, it was easier to do it. It was easier to work with this when you get rid of those values. And what you have here is the list of the values that we have from Ansys. If you look at the array parameters and you go to define it and you look at FRS, you will have the same values. It's just more complicated to work with these menus here. So we wanna quit. We don't want to make any changes, and this is how we list the values. There's an option in Ansys to plot stuff, to plot graphics. So we want to do and plot array tables, and the name on the X we would like to have stiffness, and on the Y we would have like frequencies, FRS. If you perform this plot, it is extremely complicated to understand because Ansys does not put points. It doesn't connect those points with lines. It just makes some kind of a step graphic in which it shows you how these values would be, but we clearly cannot work with this kind of stuff. So I'm going to show you how to obtain the graphic in Excel. So I'm going to get here, I have an Excel spreadsheet opened. So what we want to do is compare the values. So on one of the columns, we would put the values of the stiffness, right? Here we have them, 1,000, 2,000, 5, 10. And on the other side, we would like to get I'm going to change this to the left because I have this command here. We can use this as status frequencies in this FRS. Here I didn't have it completely. I just copy it. 1 second. FRS. 1 to 7, which is exactly the same command. It will do exactly the same as what we had with listing the value. So you can copy this text file, open it in Excel, but because it's a simple situation right now, I'm going to look at this. I'm going to type these values. So 1.4235, 2.2507, 3.1830, 5.0329, 7.1176, and 9.0031. So as you can see, along with the stiffness, the frequency increases. So the more increase on the stiffness, a bigger increase on the stiffness. Now you can plot the results, and you can check exactly how this behaves. And as you will see, an increase on the stiffness, the variation between the stiffness and the modal frequency, it's not direct. As you can actually see from the equation is a square root, and it has a direct influence between the omega and k. We can check that, you can verify that very simply if you just put a couple of random numbers, like in series, 1, 2, 3, 4, 5, 9, let's put here 5, 20, 50, 100, 200, and we're going to do the square root of those numbers. We're going to calculate the square root of those numbers in series, and then we're going to plot them too. So we're going to insert a scatter graphic, and as you can see, we obtain a very similar graphic. You could have obtained these results, or you could have understood the results by just analyzing the equation. But what we show you today is how to perform this type of simulations in Ansys APDL in order to understand the results, or more complex models in order to understand the results in a more scientific way that will allow you to perform more complex and more detailed simulations. So we hope you enjoyed this tutorial. If you did, please subscribe to our channel and like our videos. And thank you for watching.